In this example, we're going to balance a redox equation in a basic solution. Guidelines for doing this appear in section 16.2 of your text, and a good example is example 16-5 on page 939. We'll start by determining in this reaction what's being oxidized and what's being reduced. The bromide has an oxidation state of -1. The bromine in the bromate ion has an oxidation state of +5. The manganese in permanganate is at a +7 state, and the manganese in MnO2 is at a +4 state. So the bromine's being oxidized and the manganese is being reduced. Let's start with the oxidation reaction. Unbalanced, its bromide becomes bromate. We see that the bromine is already balanced. We don't have to do anything about that. But the oxygen is not balanced, so we add enough waters on the left-hand side in this case to bring the number of oxygens up to 3 on the left and on the right. Now the hydrogens are not balanced. We have 6 on the left and none on the right. We balance those in a basic solution by adding 6 waters to the right and the same number of hydroxides to the left, 6. So at this point the bromine and the oxygen and the hydrogen are all balanced. I'm going to cancel out 3 waters on each side, leaving 3 on the right. And then I'm going to balance the charge. Note that the charge is -7 on the left and -1 on the right. So if we add 6 electrons to the right, we have a balanced oxidation half reaction. Now let's move to the reduction reaction. This is the reduction of the permanganate ion, a very strong oxidant, to manganese dioxide. Again, the manganese is balanced here, so we don't have to add any coefficients to balance that. But the oxygen is not, so we'll add 2 waters to the right-hand side, such that there are now 4 oxygens on each side. To balance in a basic solution, you then look at how many hydrogens there are, in this case 4 on the right-hand side, and you add that same number of waters to the other side. So we add 4 waters to the left and 4 hydroxides to the right. At this point, the manganese, the oxygen, and the hydrogen are all balanced. I'm going to cancel out 2 of the waters on each side. And then I'm going to balance the charge. Note that the charge is -1 on the left and -4 on the right. So I balance that by adding 3 electrons to the left-hand side. Now the charge is -4 on each side. So we have balanced oxidation and reduction reactions, but note that the oxidation reaction is releasing 6 electrons, whereas the reduction reaction is taking in 3. We fix this problem by multiplying the reduction reaction through by 2. And then both the oxidation and reduction reactions have 6 electrons. And when I add the 2 reactions together, the electrons cancel. They must cancel in a redox reaction. There can't be any residual electrons. When I add these 2 together, it's bromide plus 2 permanganate plus water, making bromate plus 2 manganese dioxide plus 2 hydroxide ions. Now, balancing a redox reaction is one example of a case where you can determine whether your answer is correct before you leave the exam hall, for instance. And I do it as follows. I set up a little table and I count the number of each atom and the charge on the left and right side of the balanced reaction, and they must be the same, of course. So let's look at this. We've got 1 bromide on the left and a bromine in a bromate on the right. As for manganese, we've got 2 in the permanganates and 2 in the manganese dioxides. Oxygens, we've got 8 in the permanganates plus 1 in the water makes 9 on the right. And on the left, we've got 3 in the bromate, 4 in the manganese dioxide, and 2 in the hydroxides for a total of 9 as well. On the left, we've got 2 hydrogens. On the right, we've got 2 hydrogens. And on the left, we've got a charge of -1 on the bromide and -2 on the permanganates for a total of -3. And on the right, we have a charge of -1 on the bromate and 2 negative on the hydroxides for a total of -3 as well. So this reaction is balanced.